is you don't get an alcohol out of it. Hang on. I did. Okay, I did hit record. All right, so remember you're making that weird three-sided intermediate. You started with this molecule. Your first step when you add the Hg, it's still not great, OAC2, that's going to basically remember that the mechanism is that mercury has a lone pair. These also come over to the mercury and you kick off an acetate group. So you wind up making this three-sided ring where you've got a positive charge on the mercury. One of the acetates is still attached. This is the second step is different. When you have them, when it was water, we just had H2O's lone pairs come into the more substituted carbon and attack and leaving group leaves. And that really is just an innocent two-step. So all of it, the only difference is if we switch out the water for something else with a lone pair. It's still going to be whatever that lone pair is attacking its nucleophile with mercury leaving. But okay, take care of that.
Nothing that they would have the government relevant.
Cool.
They would call you to remind you about it's like just to make the check. See, I know, but it's time like I know these things. You know, you can like check in online before so that they can. Well, yeah, but it's still not even until Thursday. It's I know they do too.
Can't even get away from it if you're just doing telemedicine. I had a telemedicine phone call between lecture and lab today, and they had to call me this morning to reschedule it. And we'll be back 30 minutes. So it doesn't matter what you do. Turns out you're gonna have to answer the phone sometimes. It's annoying, but so I'd rather people call me than I have to call it. That's a personal anxiety thing. I keep calling. Yeah. All right, so then your net result, if it's water, looks like this. If it's ethanol instead, it's still a lone pair attacking, and you're still going to wind up with similar looking intermediate. It's just now we're going to kick off this hydrogen, so we get a third instead of an alcohol. So makes a different functional group, but really the mechanism is the same. And same if it was a nitrogen, you're going to wind up making an amine with an active group on it. Anything with a lone pair can really do the second step, any nucleophile. So you can even see something like a sulfur. Okay. It's just a little bit, you're not going to get as good a yield and it's less common. Read this up there because it's not really in the way. These quiz questions. One of them is a hydration, the other two are still addition reactions called hydrobromation. So those were the first one. Yeah. I'm sorry. Yeah. No worries.
Oh, we did look up those.
We started with them before we brought in water.
I was looking for my other habit. I think my best cat's on my head.
That's okay. So for the acid catalyzed hydration, it looks like we've seen before. You start with an H plus gets grabbed by the pi bonds. So you get an intermediate that looks like this. So we added the hydrogen, drawing in the new hydrogen, the rest of the skeleton structure. Which, and then our next step normally would just be, okay, now water acts as a nuclear bond and attaches to that positive charge. Except we can do a rearrangement. Then the water comes in. Then we get a water molecule with that, and then it's just a quick proton transfer to clean it up. So final product is any stereochemistry to worry about this one. R versus S, system trans. You think correctly.
Okay.
It's always worth thinking about, right? This carbon's not a stereo center because both directions are on the ring right. There's no system trans because there's nothing else attached to the ring. And this carbon has two identical metals attached to it. So the mechanism is the same as HBr. The only difference is in the nucleophile attached step. We just have a bromide that's going to act as a nucleophile instead of the water. So if anything, it's a little simpler. Your first step is going to look like this. Proton transfer breaks up the pi bonds. And our new hydrogen is right here. We're always going to put the positive charge on the more substituted carbon, right? That's what leads to that Markov-Nikov rule, is that a secondary carbocation is more stable than primary. So if you're going to make a carbocation, it's going to be a secondary carbocation. If you have a choice. And then in this case, we have that one more wrinkle because it's a carbocation. We have to think about rearrangements. No proton to transfer, but we could move a metal over. So this one, as I mentioned, this one's not hydration in our water molecule. Both of these two are hydrobromination. It is. The reason we don't just call it bromination is because bromination is when we're going to add two bromines. That's going to be one of the next ones we add in on Thursday.
So hydrobromination is the hydrogen on one side and bromine on the other. Why come up with new words when you can just slam old words together? It's the German style of naming things.
I mean, honestly, it's nice this way, you don't have to like remember vocab words, you just have to pick it apart.
Right. Which also incidentally serves you well on standardized tests like CAT, or I don't know if dentistry has their own
Yeah.
DAT. One of the study tools, one of the test taking strategies they teach you is know your Latin roots, your Greek roots, because they show up everywhere. And you can get a halfway decent guess if you don't know what they're talking about.
Yeah.
Which I don't know if it was. High school gets a little hazy for me. It's getting kind of back there in history. I don't think I took an SAT prep, but I remember I think I like sat in a class or something like that where they talked about that, and then that might have been where I really started paying attention to that sort of thing.
Yeah.
But none of that happened to me. All right. And even so, it wasn't until after I named my daughter Venus that I came up with when I realized I'm covalent. Covalent means it's in two valences at once.
What did naming your daughter, like, how did that?
I just started thinking about that word and the root of it more. And so that sort of triggered that connection for me. She has her second basketball game. Over at Kale. That said, you didn't grow up here, so you didn't do community basketball game. It's a big deal in town. Their first game, I think they won 8-6 at their local place.
I don't remember playing best.
Every basket is 2 points, so 8-6 was not very many baskets over about an hour. All right, so this one is even easier because there's no rearrangement that's going to happen. First step is add the hydrogen and make carbocation.
Why can't I just the hydrogen?
Because they've done some studies on the rates of this reaction where they can prove it doesn't happen. So let's think about that. If it happened all at once, we're gonna deal with we're gonna see actually a mechanism step today where we add something with both sides simultaneously. We know that's not gonna happen here. Are you good if I put it board here?
Yeah.
Because we see very specific stereochemistry if that happens. If we had a pi bond,
So are we always designing with H first, or is it going with the?
basically because we can do this is actually a perfect example. If it happened all at once, we wouldn't see any rearrangement happen. Right, because if it happened all at once, we'd be adding hydrogen to one side, bromine to the other. Might look something like that.
If it happened all at once.
If it happened all in one step. Because so the pi bond grabs the hydrogen, the bromine gets to hold on to the electrons that were part of the hydrogen bonds, and one of the other lone pairs on the bromine is going to attach to the other carbon. We would see very specifically no rearrangement happening if that was the case. So the fact that we can do this reaction and we almost exclusively see the rearranged products tells us it has to happen in 2 steps. Because so anytime you see a rearrangement, you have to be going for a carbocation intermediate. Rearrangements don't happen if we have a concerted reaction, just like when we studied SN1 versus SN2 reactions. We didn't worry about rearrangement for the SN2. Just moving this one up so that I can, it's easier for me to write, but higher. So we make the carbocation intermediate. Comes in and attaches. Where the positive charge is. Ooh, too many carbons. We're gonna get just this product. So these mechanisms are a little bit, they're a little bit like the first time you see an algebra trick in a math class, you would never come up with it on your own. It kind of makes sense the first time you see it, but you have a hard time replicating it. But the more times you see it, the more times you can see the patterns start to show up. And you'll start to see it more intuitively. It's going to take a little bit of practice, but it'll start to feel more and more natural the more we work on these mechanisms. So let's look at the other mechanism. So here's our oxymercuration. If we just want product, we just have to know, okay, oxymercuration with water is going to be a hydration. So we had an OH. And you can start just keeping track of, instead of writing out the full mechanism, you say, okay, it's hydration. And it's Markovnikov. So I'm adding the hydrogen to one side and OH to the other. I'm putting the OH on the more substituted side. There's no rearrangement. These are just sort of the variables to keep track of. And anytime you see this mercury, that's what you should be thinking. Hydration, Markovnikov, no rearrangement. The only time it's not hydration is to switch out with the nucleophiles, so it's going to look substantially the same. So our net result here winds up being I would feel about that. Okay. So similar addition, it's not technically hydration. It's an ethanolation. Okay. But still Markovnikov, still no rearrangements. If we want to see what the mechanism, the intermediate looks like to help us with the mechanism. We got our acetate group attached to the mercury. No rearrangement.
because it makes this three-sided ring. Three-sided ring basically means you don't have a full carbocation, so you don't have an empty spot in that carbon for things to move into. Then on the more substituted side, your nucleophile comes in, pushes off the mercury. And then we're gonna just reduce it to get rid of the mercury, so we'll wind up getting an ethoxy group attached on one side of the pi bonds,
And the hydrogen gets attached to the other.
you might notice that I tend to keep the same abbreviations, but I wanted to just write this out, the final product out like that, means the same thing. But it can be helpful for keeping track of where stuff is, where did my reactants go. Anything really change here?
That one I really wanna go over, cause I need.
Okay.
The nitrogen. Well, like I tear up the whole thing and I don't. Try. I think that was.
This one
Yeah,
can,
it's mechanisms all the way back. That.
This is definitely one we're showing the mechanism of you because of the stereochemistry. Because we're gonna initially start by. We have to think about what's gonna happen to those methyls when we attach our mercury, right?
And how do you know if it's gonna be more calm?
Because everything we've looked at so far is Markovnikov. Markovnikov is the standard case. Usually when you do an addition reaction, you're adding your nucleophile to the Bohr substitute. There are a few anti-Markovnikov rules for our reactions that we're gonna go over today. But for the most part, you should be thinking with your negative charge is gonna be attracted to Bohr substituted carbon. So we're showing the mechanism here. Basically pick one of the two carbons for the mercury lone pair to attach to. Pi bond attaches to the mercury. One of the acetate groups gets kicked off. Because this one has a ring structure involved, though, now we can think about stereochemistry. If we're gonna make that three-sided ring, what do we know about the methyls in the intermediate? Are they gonna be cis or trans? Relative to each other?
Because instead of writing that always cis.
Because if the mercury is part of a three-sided ring here, the mercury has to be cis relative to itself, right? You can't have the mercury make a three-sided ring on both sides of the ring simultaneously. That's just not how space works.
Yeah.
So from a sterics point of view, basically your mercury comes in from one side of the ring and pushes the two metals to the other side. Now, we hadn't covered the stereochemistry for this, so creating this one, I'm not gonna grade you on getting the stereochemistry. That wasn't the point. It's just to try and get you some practice drawing these kinds of products. So for the next step, it's an ethylamine. This ethylamine, the nitrogen has a lone pair. That's what's gonna be our nucleophile. It's an SN2, so we're gonna see an umbrella flip here. Remember talking about the SN2 substitutions where their stereochemistry flipped because that backside displacement? Because if the mercury is sticking up, this lone pair has to come from behind to push the mercury away. So we're gonna get an intermediate that looks like, now we've got the mercury still up on this side and the methyl down, but now on this side, the methyl is up and the nitrogen is down. So then if we do a little proton transfer to clean this up. Yes, looks like that. The other thing to think about here. And this is really getting into the splitting hairs territory. Is that this nitrogen could have attacked either of these targets, right? So you get the other stereos if you attack the other carbon. Because then you would get the mercury attached on the bottom and the nitrogen attached on the top. So it would look something like HGOAC, methyl down, methyl up, ethylamine into the board. So big, just that one flipped. Just the stereochemistry or the stereo. So I'm going to stick with drawing the purple one. Because it's definitely one where at the end of it, you could also just write draw the mechanism once and then write plus and get. Last wrinkle with this one. What is the step? We know that the last step is kind of hand waved it, right? It's linked very well. We just said, well, we've got a reducing agent, so it reduces the mercury and replaces it with the hydrogen. If we don't know what the mechanism is, what do we know about the stereochemistry though? And that's something that even second year OChem textbooks don't get into the stereochemistry of this reaction very much. Because basically what's going to happen that NADH4 step
is gonna have it go through two stereochemistry inversions. Basically gonna flip the methyl up, then flip it back down. The net result is basically, you can do that, right? Wherever the mercury is where the hydrogen is gonna get added in the same configuration, same stereochemistry. All right, and if you, my go-to resource for when our textbooks aren't enough is Master Organic Chemistry, which we used a little bit last year. Let's see, mercuration.
This is actually really, this is almost exactly what we just looked at, except we had, right? Then the next step was, it's called a ring opening reaction, when you attack it with the nucleophile, because you have this strained ring, so we bring in the new one. And when we do that, and then the demercuration step. So that's, it's talking about the process from our Markovnikov reaction. Oxymercuration. We want the demercuration. So you can say there's a lot of detail in here. Figures don't look quite as polished, but they're also very, very in-depth. This is the step we're looking for. So in this case, I take it back. With stereochemistry of the CH bond, carbon mercury bond is not perfectly conserved. So basically, you're going to get a mixture on the carbon where the mercury is attached. So the second step.
Mixture of what?
Both enantiomers. So you're going to get, we had the mercury attached here. Sorry, I just misremembered that. I explained it very clearly wrong. Where the mercury is attached after the ring opening reaction, that carbon loses its stereochemistry. So right now we've got the methyl down and the mercury up. After we do this next step, we're going to wind up with a mixture of, so methyl, methyl up, and then on the other side, there's our amine down plus methyl down and amine down. I left off that part in there. So this bottom carbon is going to stay the same once we do the ring opening reaction, but we're going to get a mixture of both possibilities. So some where the methyls sit relative to each other, some where the methyls are. And this is one of the reasons why with the textbook that I mean waves that's a mechanism, because it gets fuzzy. It's not as clean. And so we're not going to spend as much time on the mechanism. And in general, because we're adding that hydrogen to the less substituted carbon, this only winds up being an issue if it's a ring structure, like we saw here, or if both carbons are tertiary. If both carbons are tertiary, you can wind up with similar issues as having a ring structure, where you wind up with a variety of enantiomers. As long as it's not a tertiary carbon, then when we add that that hydrogen to the less substituted carbon, we're gonna lose our stereochemistry anyway, because we're not gonna have stereos. So this is really splitting hairs and getting into the nitty gritty of a very small niche of reactions. But because I started this class off by saying we don't have to wait things anymore, and we get to dive down as one. Now, worth thinking. So we're actually gonna get 4 stereoisomers for this one. We get 2 stereoisomers from that purple route, and then 2 stereoisomers here. We get all 4 of the di, we get 2 enantiomers and then the diastereomers as well. You remember that term back all the way from midterm last quarter.
I remember using.
It's nothing to worry about. No, I know that this one is a bit of a wake up call in terms of mechanisms can get really nasty. So before we add another mechanism, any other questions about the quiz?
Okay.
Okay, let's take a break then.
Okay.
Let's come back at, we can take a little bit extra time. Let's come back at 5 till.
Okay. You can use the restroom. There was some things available.
Are you cold? I'm not sure. This room historically has a problem being too hot,
Oh.
so it could have. No, it says it's 74 in here.
That's like, wow. I just think like that's not.
No, sorry, it's 74.
Oh,
It says it's 72.
I don't believe it, but I believe that's set. Well, it's set.
Well, as we've seen in lab, thermocouples obviously can tend to drift a little bit
Yeah.
if they're not calibrated properly, so. All right, let's do one more mechanism. This one is going to be the classic anti-Markov hydration. So we're going to have three hydration mechanisms after this. We're going to have hydration Markovnikov does rearrange, hydration Markovnikov no rearrange, and then hydration anti-Markovnikov. I believe what I've done in the past is starting the midterm for this class, and I think that's when you get halfway through the term or through the whole series. Is when I started giving you a page of notes. So you can make your own cheat sheet.
Is one of those things, is like, I don't think know how to compare them.
We're gonna keep adding more. So, but what I would say is just keep in mind, what type of addition. For if it's an alkene, it's gonna be addition. So it's either what type of addition, Markovnikov versus anti, and rearrangements. Those are the variables to look out for. You should learn to recognize clues. This one doesn't convert mercury, so it's not awesome configuration. So it's going to be.
That may be rearranged.
Oh, basically, if it makes a carbocation intermediate, you have to worry about your.
But it, you know.
That's where kind of getting fluent and maybe even flashcards would help with, what mechanisms have a carbocation intermediate might be helpful. It's just going to take some time and some studying. But it'll start to, it's not necessarily something at this point that you can reason from first principles. It's going to be a little bit of memorizing what characteristics go with which mechanism and what the clues are. Figure out what mechanisms. So I've seen students make flowcharts. So a series of yes/no questions to try and make some of this work. But once we get through this mechanism, this is going to be. There's a couple more mechanisms for alkenes that potentially could show up on the midterm, but the bulk of what's going to be on the midterm is going to be alkenes and alkynes. So in a lot of alkynes turns out to go through really similar mechanisms. Triple bonds. You can do it. I'll remind you, you felt this way about the midterm last time. And you got 94.
That's true.
So you know how to study for these tests. It's a lot of work. I will also say the same thing, same advice I gave my Chem 100 students yesterday. Because they were also nervous about the workload of having to both work and take a whole bunch of science classes at the same time. Part of the reason why science and STEM degrees in general are so highly valued is because it's not just that it shows you know a lot about biology, it's also that it shows you know how to work and learn something. So it's hard, but if you're going to get good habits out of it. Right or wrong, if you have a chemistry or a biology degree,
that's unrelated to the job you're applying for, that'll get you further than a comparative literature degree. I like comparative literature, don't get me wrong, but it's just not the same workload and type of analytical thought you get with a science degree.
Yeah.
All right. So let's talk about this. So your clues are, we're starting with boring in THF solvent and a polar aprotic solvent. So boring is BH3, which is kind of a unique. This shows up in the mechanism here in a second, but boron is kind of unique in that it can have a neutral molecule that doesn't have a complete valence. Turns out boron and aluminum are pretty much the only stable molecules that you can do that with. And what we see when we do this isn't one where we're going to switch out what the nucleophile is. We basically just use this for hydration. The net result when we do this is that we put the OH group on the less substituted carbon. And this one is very stereospecific. You only get the syn addition. So syn is sort of like saying cis. Syn addition means that the two things you're adding go on the same side. And so this is a classic, this is a really good example reaction to this because it shows you kind of all the wrinkles. The two things that you're at, so the hydrogen are on the same side of the ring. Check and see if it sounds like they give a hard time for being loud, but I don't know the whole time. And so the opposite of syn addition is anti-addition. Anti-addition would be you add when you add two things that are at the opposite sides of the ring. Syn addition means they're added to the same side of the ring. Or it's just another vocabulary we're going to start using to describe these things. You could also say we're adding the cis relative to each other, but syn is just a shorter way of saying that. They're added to the same side of the ring. So you see the red atoms here are the ones that were added in this addition reaction. They're either both going to be sticking up or both sticking down. Part of the reason why we don't just say cis versus trans with this is because we don't usually think of hydrogens when we think of cis and trans. We think of what the other object is. So syn addition gives us a trans product because one of the things we're adding is hydrogen. So one of the reasons that we pay attention to that is because this is how we figure out these mechanisms and what steps go in what order and whether they're concerted or stepwise. It's because if it's stereospecific, it must be because it's going through some very specific reaction and or intermediate. So the fact that we don't see the anti-addition tells us some information about the mechanism itself. So this is the syn addition on top because the red ones are both on the same side.
both sticking up or both sticking down. We specifically don't see the anti-edge. Alright, so similar to mercuration, demercuration, hydroboration and oxidation has two steps. Hydroboration followed by the oxidation. Oxidation is very similar to the demercuration, where it's basically this is, and then we remove it. We're gonna start by adding boron. And then second step is removing boron.
Okay.
Right, so the first step is a little bit different because like I mentioned, boron with an incomplete valence is neutral. So it actually, when we have this, boron is less electronegative than the hydrogen. But it's also trigonal planar and has an empty valence. So it's basically, it's got a spot. I'm gonna say that that's a typo. I think that those charges are reversed.
The boron should be positive.
The boron should be positive. The negative charge goes with the hydrogen, because the hydrogen is more electronegative than the boron.
Yeah.
So the hydrogen is a partial negative. And then it's attracted to the more substituted part of the alkene. And that's mainly going to be for steric reasons. The boron is bigger than the hydrogen, so for the most part, you're going to wind up with your hydride being added the more substituted carbon. You notice it was 100%. If I go skip back a couple slides, it's like 90%. So it's not perfect. And we can even tweak that a little bit based on sterics, what else is around or what temperature we're sitting at. So it's not perfect. That's one of the reasons that kind of hints that it might be sterics. Because it's not 100% of the time it goes this route. So we get this intermediate, and I think we used this symbol before. So that symbol is basically, that's a way of saying this is a transition. So we don't always draw the transition states in our mechanisms. It's just showing you physically what this looks like when it's in between our starting material and our intermediate. Right, so we get this middle state where we got boron hydrogen bond breaking, boron carbon bond forming, carbon carbon pi bond breaking, carbon hydrogen bond forming, all at the same time. Right, if you're interestingly enough, if you're looking for what that symbol is called, it's called a double dagger. Because the classic way of drawing it in more detail actually looks like two swords pointed at each other. Old typographical symbol that for whatever reason they picked to represent a transition state, probably because that's not very stable. You try to balance a dagger or point on point. I have no idea why, but I always found that was interesting. You look for a double dagger character, it looks kind of like that. And in chemistry, it just means transition state. All right, so after this first step, oh, I see why they showed it like this. They're saying that this is an intermediate where you get partial, where basically the boron sort of attaches to the pi bonds because it has that empty valence. It's pure boron, you're going to have the partial positive here, and
partial negative here, but they're saying basically that this boron belongs onto that 5 cloud. Alright, so with that in mind, the net result of this first one. Yeah, there's a lot of arrows that you have to draw. All kind of happening simultaneously, but it's just you add a hydrogen to the more substituted carbon and the rest of your boron attaches to the other carbon. Alright, so if we're drawing mechanisms, if I ask you to draw a mechanism, you just show it like this.
I represent like vascular development.
Bond breaking or forming are shown as dotted lines.
So to add hydrogen to the substituted carbon instead of less of the boron.
To the less substituted carbon. So in this case, the way it's drawn here, you're breaking a boron hydrogen bond to make a carbon hydrogen bond. And you're breaking a carbon carbon pi bond to make a carbon boron bond. One of the weird parts about this though that we'll see this show up a couple different times. Basically, this boron, once you do this first step, if this boron still has hydrogens attached to it, so it actually does this 3 more times or 2 more times.
Are we expected to draw?
Doing it like this is fine. So frequently, if the same thing happens multiple times in a row in a mechanism, you'll see this, an arrow and an arrow. And you just say ×2, basically. And the net result is you started with an alkene and boron, and now you have a boron that has 3 of that same molecule attached to it. So if we were drawing this more completely, it would look like that. But I think it would be the carbon extra carbon. Oh, that's fine. Because of the hydride. And so basically just took this molecule and attached it to boron 3 to get it
It happens.
2 more times. Yeah. And so then we get this intermediate called a trialkyl boron, which is just this. Your carbon's got attached 3 times.
Swivel.
They're just saying, so anytime you say what, they're just saying the entire R group is this attached to something else. Swiggle is just basically saying that. Right, and this is just a figure showing that it is in fact Ceres. And we're thinking that it was the Ceres. If we go to the anti-carbon composition, when we do this step, our boron is going to go to the less substituted carbon. Just because there's less stuff in the way. In your hydride, it's added to the more substituted carbon. Just for steric reasons, so that we don't get something that looks like this described. And so weird doesn't necessarily not make sense, but it's not what we would call with underarm.
Yeah.
which is why you're in this class instead of just reading a textbook on your own. So here's our cleaned up oxidation. Okay, so this is the second step. First step is you make that dry alkyl chlorine. Second step is tricky, and if you remember, it was H2O2 plus a hydroxide. So really nasty conditions, really, when you think about it. Hydrogen peroxide is already toxic, and then we're going to put it in strongly basic conditions as well. We're basically going to take hydrogen peroxide and we're going to deprotonate it. So we make a peroxide ion. Hydroperoxide ion. So all the worst things about peroxide and hydroxide in one molecule. It's kind of nasty. The advantage to that though is you can use that oxygen, then it's a pretty good leaving group. And it's going to attack that boron pretty strongly. So we basically get this peroxide attached to the boron. But because an oxygen-oxygen single bond is so unstable, you basically shift one of your R groups onto the oxygen and kick off the hydroxide. So we started with proton transfer to make this really nasty thing, which then does a nucleophilic attack boron. And it doesn't have to pick anything off of the boron because the boron already has space. Then we do a rearrangement. Where rearrangement and leaving group leaves really want to be. We're tracking all of these arrows simultaneously. Your R group rearranges onto the oxygen, the second oxygen, then can take the electrons to go. So we get this then. Basically, these first 1, 2, 3 steps are just our way that inserts an oxygen atom between the boron and the R group. And then 2 more times. Thing is that boron is at its most stable when it's completely oxidized. Because its electronegativity is so low that it's going to continue to be a target for other really electronegative ions. So then once we get here, we're going to basically do nucleophilic attack leaving group leaves 3 times in a row. It's just that now your nucleophilic attack is just the hydroxide. Hydroxide jumps on there, right here, and then leaving group leaves. And 2 more times. Let me shrink that figure down a little bit. And so we can see the bottom one step more completely. So hydroxide attacks, leaving group leaves. Hydroxide attacks, leaving group leaves. Hydroxide attacks, leaving group leaves. Then we just have all of these deprotonated alcohols floating around. We just do a proton transfer to finalize. That's a lot. I recognize that.
Okay.
Especially since this is just step 2 of an already weird reaction involving boron.
Yeah.
So the key to remembering this is to remember what your landmarks are.
Okay.
By which I mean, if you can kind of remember, okay, I didn't necessarily memorize all of the arrows, but I know I need to get to this. And then from here, I don't remember necessarily what all the arrows are, but I know that I'm gonna get to this. Then you're filling in smaller gaps.
Right.
The first time I started learning these more complicated mechanisms in OCAM, I'm like, oh, all the steps individually make sense. So I don't really need to memorize it because I'll just logic my way through it on the test. The problem with that approach is because I didn't have my landmarks that I was headed towards, I went off in totally different directions and got lost. So it's a lot like trying to remember directions when you're driving. You don't need to know every turn in the road between here and Placerville.
Right.
You just need to know, okay, I'm passing, that Apple Orchard Cafe or whatever it's called, it's closed. I
Yeah.
know I'm most of the way there. I know I'm going the right direction. Right, so if you can remember what those landmarks are, that makes it a lot easier to sort of fill in the gaps.
Give me like a test.
Yeah, no problem. We have time. If you don't ask for extra time when you need it, we finish these slides too early and just leave and be lost. So.
And we're gonna practice this.
We're gonna practice this right now. At the very least, do the process.
Yeah.
The net result of this is, these were our
What are the variables to think about?
what type of addition is it?
Is it Markov-Makov or anti? Can it do rearrangements?
As soon as you see this combination, boron and then that hydrogen peroxide, you should be thinking it's a hydration. It's anti-Markov-Makov. So I'm adding, and hydration means I'm adding hydrogen to one side and OH to the other. It's anti-Markov-Makov, so I'm adding my OH to the less substituted side. And it can't go through any rearrangements because there was no carbocation at any point in our mechanism. So there's a problem.
What is the pH?
That's just the solvent. The boron has to be hydrofluoric because it's a specific polar aprotic solvent that will dissolve the boron without reacting. Luckily, we still haven't dealt with any mechanisms that or reactions that change the carbon structure, right? The carbons are all staying where they are. So at the very least, start by running up the carbons, right?
We're gonna break the pie down, add hydrogen to one side and OH to the other. Which side gets the OH? The right side.
Why did you put one? Oh, wait, never mind. Oh, wait. I think I do that, just like we talked about. I just saved it for my brain.
Alright, so for C. Draw your carbons. We're adding an OH, breaking a pi bond. And it's anti-Markovnikov. So we're putting the OH on the less substituted carbon.
So all of these are, and
Anytime you see this mechanism will always be anti-Markovnikov.
okay,
So that's, when I'm talking about these three questions,
yeah,
we're looking at the specific mechanism. Each mechanism is always gonna have those wrinkles. So oxymercuration will always be hydration, it will always be Markovnikov, it will never rearrange. No matter what the starting material is.
these are the anti-mark. Wait, which one? That's the
This one will never rearrange, and the oxymercuration will never rearrange. The only one that rearranges is that first acid catalyzed hydration.
very.
Correct.
The rest of river reached. It's just not so over like no family.
That's fair.
So we did ranges to be on with Calvin's office. Oh, I, okay, it's Mark. He's big Mark.
Mark,
I was just gonna do like a Mr. Ed, like this. Mr. Ed. It's gonna be someone else. Yeah.
there you go, what's it, so you don't have to worry about Mr. What's. You guys watch Stranger Things.
And like I had to rewatch all of it because it was too long ago, but I'm also too scared to watch it at nighttime. So I have to watch it during the day, which is really hard to do. I just never seen it because when I was like 12 when I first came out. Really nice.
Dash is watch the first episode, I want to watch.
I watched the last episode.
You watched just the last episode.
Pretty boring and confusing.
Yeah, it wasn't great, I'll say that.
It's horrible now. Oh, it's Chef. Skip a lot of conspiracies online, to, like try and make people feel better about it.
Yeah, it was,
Last episode.
it is interesting, anytime you have a long running show that people feel very strongly about, the finale is always gonna be controversial. Game of Thrones had the same thing. I didn't think Game of Thrones ending was that bad, but people hated it. It did, a little bit.
Because they got more the book and they get like this all down and it's waiting.
Yeah, well, except that George Martin's never going to finish those books. So he will done. And then somebody else will finish, but it won't be him finishing it. Have you seen the guy? He's like 350 pounds, 70 years old. He'll die soon.
See that occurred.
Yeah. Anyway.
I just really liked the emphasis.
It's the same thing happened to Frank Herbert, the author of book two. He died, and then his son and another sci-fi author kept the series going after he died. Which is what I'm anticipating will happen. Anyway, if we wanted to draw the mechanism here without rechecking our notes the entire time, you can do that. That's totally fine. I don't have the whole mechanism pressed. But I can get there because I know on the roadmap. That's the first thing I need to do is I'm gonna make an intermediate that looks like this. So 1, 2, 3, 4. Yeah, that's ready for purpose. I know I'm gonna make this. So how do I get there?
Right. We're doing A.
Just do it. Just I pick the smallest one. Although it might be easier if I pick the one that's next on. We'll do the middle one.
B.
B.
Okay.
Just because I'll be able to keep track of the right number. A little bit better since it's over here.
So.
So the first step.
Right, we're switch.
You do the weird switch thing. So now we have. And then it does it 2 more times.
I'm not allowed. And it's both.
I would call that the last song. All of my alkyl groups that actually were on. That's one. That's the hydroboration part. The rest of it was just oxidation. You put it in a strongly oxidizing environment, does a couple of rearrangements, and you wind up making your final product.
Where did I process?
We did the same thing. Remember, we saw put 2 arrows back to back. We did this first step 3 times.
So like, when we're looking at these, like how in the past you've really been looking at one individual one, now we're kind of have to pretend that it's all swirling around in substance.
We remember that you actually have a whole bunch of this happening at the same time. And if we're actually making this, doing this in lab, I believe that we do this in a 3-to-1 ratio. We only need 1 mole of chlorine for every 3 moles of this molecule. But again, OChem gets sloppy with the balancing because we mainly just care about this. Whatever else we have to react it with, this is what our final product is going to be.
Right.
Because it's part of it and we ignore everything that's not part of it.
That's not the end.
It's not yet, that's the end of the first step, that's the hydroboration step. We have hydroborated. And the second step is. We have. Hydrogen peroxide. And hydroxide. Basically, hydroxide is a stronger base than peroxide is. So we make this hydroperoxide ion that is super strong, super reactive.
We like can never work with this one. This is like substances that we're not.
I mean, this would be in the fume hood, gloves, goggles. The nice thing about it is it stays dissolved. Most charged things are going to stay in solution. So as long as you're careful to not spill any on you,
wearing gloves and lab coats and everything, you actually can work with it.
The state allows.
The state allows.
I have a question actually. With
Yeah.
that, why do they not like raincoat material, why do they absorb?
One, because it would get really, really hot, sweating
Okay,
to wear that. And there are some labs that work in with suits more like that. But lab coats are made out of cotton for the most part because cotton reacts similarly to your skin. Because it's cellulose, right? So it's just based, it's still carbon based, similar to your proteins and stuff in your skin. And so that I think the thinking is that one, it's absorbent, and then two, it's similar enough so that everything will react before it gets through the cotton to your skin. And it doesn't dissolve in solvents. You can't use something like polyester because if you get acetone on polyester, it dissolves. And if you get polyester too close to a flame, it melts. So you really don't want flaming dissolved polyester on your skin. So and same true with most synthetic fabrics. So cotton is really useful in that it's a good buffer that slows things down. In real, the first thing you do if you spill a large amount of something on your cotton lab coat, take it off as fast as you can, hopefully get it off before it gets through.
yeah,
But we don't want to use something synthetic because most synthetics have these other issues.
thank you.
Yeah, no problem. This molecule would not be a problem for synthetic supply.
Okay,
But if you did this with heat in your synthetic cotton fiber, it'd be a problem. So things like that. All right. Once we have our hydroperoxide ion. It just jumps in there.
slowly grow.
Because the second step is hydrogen peroxide in sodium hydroxide solution. So yes, it is. We add in the second step. We add this. So now we get this purple intermediate, which is just going to do a quick rearrangement. This hydroxide is a really good leaving group, especially because its oxygen single bond is so weak. So these two things shift over, and the leaving group leaves. And now we still have two of those look the same. We just effectively inserted an oxygen between the boron and the first carbon. And we're going to do that 2 more times.
So then you have one where all of the reactions have the oxygen for the.
Exactly. It looks just like this, but all of them have oxygen in there too.
if you're ever unsure, if you lost the carbon or gained the carbon somewhere, just go back to your starting material. We started with a pentagon plus one extra carbon. We still have a pentagon plus one extra carbon in each of these. So that's our next landmark. Our first landmark was getting to our 3 R groups attached to boron. Second landmark is our 3 R groups but with an oxygen attached. Then the last step is that hydroxide that's floating around continues to react with boron. Not good. So for one, we're starting with a bunch of hydroxide floating around. We used up part of it, but then in this step where we had that oxygen single bond, we actually made more hydroxide. So we didn't have a bunch of hydroxide. Yeah.
Is that? Where did we start? It's raised. No, I mean like, like once we had our boarding with our 3 options and thousands. Where is that? What did we, okay,
Once we get here, hydroxide just comes in. Remember, we got here because we had oxygens coming in and attached back to the boron anyway. There's still hydroxide there, so they're still just gonna come in and attack the boron.
okay, so then the black one's the next.
Correct. Once we get here, remember, boron is pretty stable with only 3 things attached to it. So once we attach an OH there, one of these is just gonna leave. And once again, we're gonna do, so then we get boron, OH, oxygen, pentagon, oxygen. Yeah, I really messed that up. Do that. So we can make sure we didn't lose carbon. Plus, our leading group allowance.
That
Almost.
or ends. I know.
We're second to last step. This is, once we get here, this is our final product, except it's deprotonate. So we just do a proton transfer to CH plus. And then it does this 3 times. Right, because we had one of the leading groups leave. And then we probated it because that should.
So. We have the three of this.
Exactly, yes.
Where arrows.
So. It's gonna do this step 3 times. So. So we have 3 of these floating around before we can then just do the proton transfer. That's why if you notice on the previous slide, which it skips, it doesn't show 3 steps full 3 times happening in a row because you're leaving group B, it just leaves it like that because it just gets a little bit messy. I would say probably the cleanest place to do it would actually be to put it right here and say this arrow happens 3 times. So we're gonna get BOH3 plus 3 of these.
So that would be 3 arrows.
You could do 3 there, or you could say. I'm not gonna get what I'm trying to say, but to make it make sense in your head, either way, you can either say that happened 3 times, or you could draw the product after it happens once. Which is gonna look like what we had first had it as, and then say 2 more times. Which then gets us to, there's 3 of these. Which then goes through the proton transfer. That would be the way that would be most consistent with how we already would be. You can see why you want to use an R for this lot, because when you're redrawing this so many times, it gets a lot easier to say, oh, R. Just say what R is, which is totally fine on test too. So you could write this mechanism the same every single time, as long as at the beginning, when you first show your R attaching to the boron, you say R equals this.
You know, those like using tutorials where they're like step 1, step 2, now off camera, I'm gonna do some shading, and then it comes to the end and it's completely different.
Right.
That's how I feel, right?
A little bit. That's fair. And this is definitely one where if you watch some other videos on it, if you read the section on the textbook, you'll start to, the repetition will really start to, okay, that's why we're doing this step, or this step doesn't look as unfamiliar to me because now I've seen it last time.
But this seems like a really simple product for all of those steps.
That's the tricky part of it, okay.
Like.
All we need is to throw it on.
Yeah, all we did was break the title out of them, but oh, let's be short.
The short thing is, once you recognize, if you don't have to draw a mechanism, don't.
just break the pylon and then put the oak.
As soon as you recognize that this is type of radiation oxidation, ask yourself those three questions, be like, boom, draw the product. Only draw the mechanisms for these ones when you have to.
If I can actually.
It's a paper. New instrument, we're talking about mass spectrometry.
Oh, right.
Yeah.
Oh, no, we didn't.
You did not. Yeah, as I recall, both of you got pretty close. You had cinnamon, right, Taylor? I think you got it right. And you had,
I was fighting for my life trying to find something that was gonna give me 5 different signals. But I tell you, I was sitting there trying to I grabbed so many different ones. And I was trying to explain it to my dad to try to help myself. Maybe something I have no idea what you're saying right now.
I first tried, I think I was in Rita trying to explain to women who.
Yeah,
That's been college,
but it helps with
So-
stuff. I'm I wasn't hitting him, I did junk him. So I'm straight and oak him. This is crash course.
you are insane, you belong in an asylum. What's happening?
I
I
was-
tried to explain to him and I was like, do you understand? He's like, no, I don't. I'm just gonna and we're gonna be done.
that's actually a technique that they teach in computer science when it comes to coding, the rubber ducky. Yeah. Rubber ducky coding is a real thing. So at least we're talking to a rubber ducky you had. All right.
And I'm like, do you understand anything? I said, it's nope, but I know I don't. I'll use this to pass fast time. They'll understand